Script for a YouTube video explaining how to find the areas of plane regions. Introduction. Opening shot of a whiteboard with a geometric shape. Host, voiceover, welcome to your channel name. In today's video, we're going to dive into the fascinating world of finding the areas of plane regions. Whether you're a student learning geometry or just curious about how to measure the space inside different shapes, this video is for you. Let's get started. 1. Understanding area. Visual definition of area. Host, voiceover. Before we jump into specific shapes, let's start with the basics. Area is a measure of the amount of space enclosed by a two-dimensional shape. It's like counting the number of square units that fit inside a region. 2. Finding the area of rectangles and squares. Visual formulas for rectangles and squares. Host, voiceover. Let's begin with rectangles and squares. To find the area of a rectangle, simply multiply its length L by its width W. So, area equals LW for squares, where all sides are equal. You can use the formula area equals side or simply square the side length. 3. Finding the area of triangles. Visual formula and explanation for triangles. Host, voiceover. Triangles are half of a rectangle, so their area is calculated as half the product of the base B and the height h. The formula is area equals 1/2 bh. Make sure the height is perpendicular to the base. 4. Finding the area of parallelograms. Visual formula and explanation for parallelograms. Host, voiceover. Parallelograms also use the base times height formula, where b is the base length and h is the perpendicular height. So, area equals bh. The height must be perpendicular to the base. 5. Finding the area of trapezoids. Visual formula and explanation for trapezoids. Host, voiceover. Trapezoids are a bit trickier, but still use the base times height concept. The formula is area equals 1/2 sum of bases, h, where h is the perpendicular height and the sum of bases is the sum of the lengths of the top and bottom sides. 6. Finding the area of circles. Visual formula and explanation for circles. Host, voiceover. For circles, the formula for the area is area equals pi r squared, where r is the radius. Pi is approximately 3.14159. This formula gives us the area inside the circle's boundary. 7. Practical examples. MPS TIN MPS, RES, RTA, S, R, S, R, C, S, C, R, S, 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 I, N, N, S, 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 N. Visual, real-world examples and calculations. Host, voiceover. Let's work through some practical examples to find the areas of different shapes, combining these formulas and techniques. 8. Conclusion. Visual host summarizing key points. Host, voiceover. To sum it up, finding the areas of plane regions involves understanding the specific formulas for different shapes and applying them correctly. We've covered rectangles, squares, triangles, parallelograms, trapezoids, and circles. Closing shot of a whiteboard with area formulas. Host, voiceover. If you found this video helpful, please give it a thumbs up and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and happy learning. Introduction. Opening shot of a whiteboard with mathematical equations. Host, voiceover. Welcome to your channel name. In this video, we're going to explore the concept of the antiderivative, which is a fundamental concept in calculus. Whether you're a student diving into calculus or just curious about how we can reverse the process of differentiation, this video is for you. Let's get started. 1. Understanding the antiderivative. Visual definition of antiderivative. Host, voiceover. So, what exactly is the antiderivative? Well, it's essentially the reverse of differentiation. Just as differentiation measures how a function changes, the antiderivative helps us find the original function when we know its rate of change. 2. Notation. Visual mathematical notation for antiderivatives. Host, voiceover. Mathematically, the antiderivative is denoted by a symbol that looks like an elongated s, and is called the integral sign. We write fx, dx to represent the antiderivative of a function fx. It's like asking, what function, when differentiated, gives us fx? 3. The constant of integration. Visual explanation of the constant of integration. Host, voiceover. When finding the antiderivative, there's one additional detail to remember: the constant of integration, often denoted as plus c. This constant accounts for all possible functions that have the same derivative. 4. Basic antiderivative rules. Visual, list of basic antiderivative rules. Host, voiceover, just as we have rules for differentiation, we also have rules for finding antiderivatives. Some of the basic rules include the power rule for antiderivatives. The antiderivative of xn is 1 n plus 1, x n plus 1, plus c. The constant rule for antiderivatives. The antiderivative of a constant c is cx plus c. The sum rule for antiderivatives. The antiderivative of the sum of two functions is the sum of their antiderivatives. The constant multiple rule for antiderivatives. You can factor constants out of an antiderivative. 5. Practical examples. MPS TIN MPS, RES, RTA, S, R, S, R, C, S, C, R, S, 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 I, N, N, S, 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 N. Visual examples of finding antiderivatives. Host, voiceover. Let's work through some practical examples to see how we can find the antiderivative of various functions using these rules. 6. The indefinite integral. Visual, explanation of the indefinite integral. Host, voiceover. The antiderivative that we find, with the constant of integration plus c, is called an indefinite integral. It represents a family of functions that differ only by a constant. 7. Applications of the antiderivative. Visual real-world examples. Host, voiceover. The antiderivative is not just a theoretical concept, it has numerous applications in physics, engineering, economics, and more. It helps us find accumulated quantities, like distance traveled, or total change in a system. 8. Conclusion. Visual host summarizing key points. Host, voiceover. In summary, the antiderivative is a crucial concept in calculus that allows us to find the original function when we know its rate of change. We've discussed its notation, the constant of integration, basic rules, and its practical applications. Closing shot of a whiteboard with antiderivative equations. Host, voiceover. If you found this video informative, please give it a thumbs up, and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching, your channel name, and happy learning. Script for a YouTube video explaining the applications of differentiation in calculus. Introduction. Opening shot of a whiteboard with calculus equations. Host, voiceover. Welcome to your channel name. In today's video, we're going to explore the fascinating world of applications of differentiation in calculus. Whether you're a student mastering calculus or just curious about how these concepts are used in the real world, this video is for you. Let's dive in. 1. Understanding differentiation. Visual, recap of differentiation. Host, voiceover. Before we jump into the applications, let's briefly revisit what differentiation is. In calculus, differentiation is the process of finding the derivative, which measures how a function changes as its input changes. It's all about studying rates of change. 2. Rates of change in physics. Visual, examples of physics equations involving derivatives. Host, voiceover. One of the most common applications of differentiation is in physics. It helps us understand the motion of objects, calculate velocities, and determine accelerations. For instance, the derivative of position with respect to time gives us velocity, and the second derivative gives us acceleration. 3. Optimization problems. Visual optimization problems and derivative equations. Host, voiceover. Calculus is a powerful tool for solving optimization problems. These are situations where we want to find the maximum or minimum value of a function, such as maximizing profit, minimizing cost, or finding the best shape for a container with a fixed volume. 4. Rates of change in economics. Visual, graphs showing supply and demand curves. Host, voiceover. In economics, derivatives help us analyze supply and demand curves, marginal cost, marginal revenue, and profit maximization. Calculus plays a crucial role in understanding how businesses make pricing and production decisions. 5. Rates of change in engineering. Visual engineering diagrams and equations. Host, voiceover. Engineers use calculus extensively to analyze and design systems. It's used in areas like electrical engineering, where derivatives help determine voltage and current changes, or in civil engineering, where it's used to calculate stresses and strains in structures. 6. Rates of change in biology. Visual biological diagrams and equations. Host, voiceover. In biology, differentiation helps us understand population growth, analyze drug concentrations in the body over time, and model the spread of diseases. It's a valuable tool for predicting and managing various biological processes. 7. Rates of change in medicine. Visual, medical graphs, and equations. Host, voiceover. In medicine, calculus is applied to study rates of change in vital signs like heart rate, blood pressure, and temperature. It's also used in pharmacokinetics to determine how drugs are absorbed, distributed, metabolized, and excreted in the body. 8. Conclusion. Visual host summarizing key points. Host, voiceover. In conclusion, differentiation in calculus is not just a theoretical concept, it's a practical tool with a wide range of applications in physics, economics, engineering, biology, medicine, and many other fields. It helps us understand the world around us and make informed decisions. Closing shot of a whiteboard with calculus equations. Host, voiceover. If you found this video informative, please give it a thumbs up and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching. Your channel name, and happy learning. Script for a YouTube video explaining derivatives of transcendental functions. Introduction. Opening shot of a whiteboard with mathematical equations. Host, voiceover. Welcome to your channel name. In this video, we're going to explore the fascinating topic of derivatives of transcendental functions in calculus. Whether you're a student diving into calculus or simply curious about advanced mathematics, understanding derivatives of transcendental functions can open up a world of possibilities. Let's dive in. 1. Review of basic derivative rules. Visual, recap of basic derivative rules. Host, voiceover. Before we tackle transcendental functions, let's briefly review the basic derivative rules we discussed in previous videos. These rules include the power rule, constant rule, sum difference rule, product rule, and quotient rule. They form the foundation for finding derivatives. 2. Transcendental functions defined. Visual, explanation and examples of transcendental functions. Host, voiceover. Transcendental functions are a category of functions that cannot be expressed as a finite combination of algebraic functions. Instead, they often involve exponentials, logarithms, trigonometric functions, and their inverses. 3. Derivatives of exponential functions. Visual derivative of ex. Host, voiceover. Let's start with exponential functions like ex. The derivative of ex is ex itself. It's a remarkable property that makes exponential functions special in calculus. 4. Derivatives of logarithmic functions. Visual derivative of ln x. Host, voiceover. Logarithmic functions, such as ln x, also have interesting derivatives. The derivative of ln x, with respect to x, is 1/x. This is a crucial result used in various applications. 5. Derivatives of trigonometric functions. Visual derivatives of sine and cosine functions. Host, voiceover. Moving on to trigonometric functions, the derivatives of sine of x and cosine of x are cosine of x and sine of x, respectively. These derivatives have important applications in physics and engineering. 6. Derivatives of inverse trigonometric functions. Visual derivatives of inverse trigonometric functions. Host, voiceover. The derivatives of inverse trigonometric functions, like arc sine of x and arc cosine of x, are equally important and are often used to solve problems involving angles and ratios. 7. Derivatives of hyperbolic functions. Visual, introduction to hyperbolic functions and their derivatives. Host, voiceover. In addition to standard trigonometric functions, calculus introduces hyperbolic functions like sin x and cos x. Their derivatives, cos x and sin x, play a key role in areas such as physics and engineering. 8. Practical applications. 2000. Visual, real-world applications of derivatives of transcendental functions. Host, voiceover. Derivatives of transcendental functions find applications in fields like physics, engineering, economics, and more. They help us analyze dynamic systems, model physical phenomena, and solve complex problems. 9. Conclusion. Visual host summarizing key points. Host, voiceover. In summary, understanding derivatives of transcendental functions is essential in calculus and has practical implications across various disciplines. We've covered the derivatives of exponential, logarithmic, trigonometric, and hyperbolic functions. Closing shot of a whiteboard with derivative equations. Host, voiceover. If you found this video informative, please give it a thumbs up and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching. Your channel name, and happy learning. Script for a YouTube video explaining derivatives of algebraic functions. Introduction. Opening shot of a whiteboard with a function equation. Host, voiceover, welcome to your channel name. In today's video, we're going to explore the fascinating world of calculus and delve into the topic of derivatives of algebraic functions. Whether you're a student tackling calculus or someone with a curious mind, understanding these concepts can unlock a world of mathematical insights. Let's get started. 1. What are derivatives? Visual, basic definition of a derivative. Host, voiceover. First things first, what exactly are derivatives? Derivatives are a fundamental concept in calculus that describe how a function changes as its input, usually denoted as x, changes. In other words, they help us measure the rate at which a function is changing at a specific point. 2. Basic derivative rules. Visual, list of basic derivative rules. Host, voiceover, there are some basic rules and formulas for finding derivatives of algebraic functions, and these rules can be applied to a wide variety of functions. The power rule, if you have a term like xn, the derivative is nx, n1. Constant rule, the derivative of a constant c is always 0. Sum difference rule, to find the derivative of a sum or difference of functions, simply find the derivative separately. Product rule, for the product of two functions u and v, the derivative is uv plus vu. Quotient rule, for the quotient of two functions u and v, the derivative is uv, vu, v squared. 3. Examples of derivatives. Visual derivative calculations for various algebraic functions. Host, voiceover. Let's walk through some examples to see how these rules are applied to find derivatives of algebraic functions like polynomials, exponential functions, and trigonometric functions. 4. Chain rule. Visual, explanation, and formula for the chain rule. Host, voiceover. For more complex functions, we use the chain rule. It helps us find the derivative of a composition of functions. The rule states that the derivative of f gx is f gx gx. It's a powerful tool for tackling functions within functions. 5. Practical applications. 2000. Visual, real-world applications of derivatives. Host, voiceover. Calculus and derivatives have practical applications in fields like physics, economics, engineering, and more. Derivatives help us analyze motion, optimize solutions, and understand how things change over time. 6. Conclusion. Visual host summarizing key points. Host, voiceover. To wrap it up, derivatives are a crucial concept in calculus that allow us to understand how algebraic functions change. We've covered the basic rules, the chain rule, and touched on their practical applications. Closing shot of a whiteboard with derivative equations. Host, voiceover. If you found this video helpful, please give it a thumbs up, and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and happy learning. Script for a YouTube video introducing derivatives in calculus. Introduction. Opening shot of a chalkboard with calculus equations. Host, voiceover, welcome to your channel name. In today's video, we're diving into the exciting world of calculus to explore the fundamental concept of derivatives. Whether you're a student learning calculus or just curious about the topic, this video will provide you with a solid introduction to derivatives. Let's get started. 1. Understanding the need for derivatives. Visual, graph of a curve. Host, voiceover. Imagine you have a curve representing a changing quantity, like the speed of a car over time or the position of an object as it moves. We often want to know how fast these quantities are changing at any given moment. That's where derivatives come in. 2. What are derivatives? Visual equations for average and instantaneous rates of change. Host, voiceover. Derivatives are a way to measure the rate of change of a function at a specific point. They tell us how fast a function is changing, or the slope of the tangent line at a particular point on a curve. 3. Instantaneous rate of change. Visual tangent line on a curve. Host, voiceover. Think of it this way. If you were tracking the speed of a car, the derivative at a specific moment would give you the exact speed at that instant, rather than an average speed over a period. 4. The notation. Visual standard derivative notation. Host, voiceover. Derivatives are often represented using the prime notation fx, or die dx if you're dealing with a function y of x. This notation signifies the derivative of a function with respect to x. 5. The derivative function. Visual graph showing a derivative function. Host, voiceover. Derivatives can also be seen as a new function that tells us the rate of change for each point on the original function's graph. This new function is called the derivative function, or simply the derivative. 6. Practical applications. 2000. Visual, real-world examples like physics equations. Host, voiceover, derivatives are incredibly useful in a wide range of fields, from physics and engineering to economics and biology. They help us analyze motion, solve optimization problems, and understand how things change over time. 7. Conclusion. Visual host summarizing key points. Host, voiceover. To sum it up, derivatives are a fundamental concept in calculus that allow us to measure the rate of change of functions. They provide insights into the behavior of real-world phenomena and are essential tools for problem solving. Closing shot of a chalkboard with calculus equations. Host, voiceover. If you found this introduction to derivatives helpful, please give this video a thumbs up and consider subscribing for more math and science content. If you have any questions or topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and happy learning. Of course, here's a script for a YouTube video explaining intermediate and extreme values in calculus. Introduction. Opening shot of a graph showing a continuous function. Host, voiceover. Welcome back to your channel name. In today's video, we'll dive into the fascinating world of intermediate and extreme values in calculus. Understanding these concepts is crucial for finding key points on a function's graph. So, whether you're a student studying calculus or just curious about math, let's get started. 1. Intermediate values. Visual, graph of a continuous function with points A and B marked. Host, voiceover. Intermediate values refer to the idea that for a continuous function, if we have 2 points, let's call them A and B on the graph where A is less than B on the x-axis, then every value between phi and fb on the y-axis must also be achieved by the function somewhere between A and B. Visual, illustration on the graph. Host, voiceover. In other words, if you can draw a horizontal line between phi and fb without crossing the graph, there must be at least one point C on the graph where fc equals the value of that horizontal line. 2. Intermediate value theorem. Visual, statement of the intermediate value theorem. Host, voiceover. This concept is formalized by the intermediate value theorem, which states that if a continuous function fx is defined on the closed interval a, b, and k as any value between phi and fb, inclusive, then there exists at least one c in the interval a, b, such that fc equals k. 3. Practical examples. MPS TIN MPS, RES, RTA, S, R, S, R, C, S, C, R, S, 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 I, N, N, S, 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 N. Visual, examples of applying the intermediate value theorem. Host, voiceover. Let's work through some practical examples to see how the intermediate value theorem applies to real functions and how it can be used to solve problems. 4. Extreme values. Visual, graph showing local maximum and minimum points. Host, voiceover. Extreme values, on the other hand, refer to the highest, maximum, and lowest, minimum points on a function's graph. These values are critical in optimization problems and identifying the behavior of functions. 5. Local and global extrema. Visual, graph showing local and global extrema. Host, voiceover. Functions can have local extrema, which are the highest or lowest points in a small neighborhood around a specific point, or global extrema, which are the absolute highest or lowest points on the entire graph. 6. Extreme value theorem. Visual, statement of the extreme value theorem. Host, voiceover. The extreme value theorem tells us that if a continuous function fx is defined on a closed interval a, b, then fx attains both a maximum and a minimum value on that interval. 7. Conclusion. Visual host summarizing key points. Host, voiceover. In conclusion, intermediate and extreme values are vital concepts in calculus. The intermediate value theorem helps us understand how functions behave within intervals, while the extreme value theorem guarantees the existence of maximum and minimum points on continuous functions. Closing shot of a graph with labeled extrema. Host, voiceover. If you found this video helpful, please give it a thumbs up and consider subscribing for more math and science content. If you have any questions or topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and happy math solving. Script for a YouTube video explaining continuity in mathematics. Introduction. Opening shot of a mathematical function graph. Host, voiceover. Welcome to your channel name. In this video, we'll explore the concept of continuity in mathematics. Whether you're a student struggling with calculus or just someone interested in understanding the smoothness of functions, you're in the right place. Let's get started. 1. Understanding continuity. Visual, graphs of continuous and non-continuous functions. Host, voiceover. Continuity is a fundamental concept in calculus that describes the behavior of a function without any sudden jumps, breaks, or holes. In simple terms, it's all about the smoothness of a function's graph. Visual illustration of a continuous function. Host, voiceover. A continuous function is one where you can draw its graph without lifting your pen from the paper. There are no interruptions, gaps, or sharp turns. Visual illustration of a non-continuous function. Host, voiceover. On the other hand, a non-continuous function has breaks or jumps in its graph, making it discontinuous. 2. Continuity at a point. Visual, graph with a focus on a single point. Host, voiceover. To check for continuity at a specific point, we use 3 criteria. 1. The function must be defined at that point. 2. The limit of the function as x approaches that point must exist. 3. The value of the function at that point must equal the limit. Visual mathematical notation. Host, voiceover. Mathematically, this can be expressed as fa equals lim xa fx. 3. Types of discontinuity. Visual illustrations of different types of discontinuities. Host, voiceover. There are several types of discontinuity. Removable discontinuity. A hole in the graph that can be filled to make the function continuous. Jump discontinuity. A sudden jump in the graph where the left and right limits exist, but are not equal. Infinite discontinuity. A vertical asymptote where the limit approaches infinity or negative infinity. Essential discontinuity. A complex type of discontinuity that doesn't fit the other categories. 4. Examples and practice. Visual, examples of functions with different types of discontinuities. Host, voiceover. Let's work through some examples to identify the types of discontinuities and determine the continuity of various functions. 5. Continuity theorems. Visual, statements of the intermediate value theorem and the extreme value theorem. Host, voiceover. Continuity leads to powerful theorems in calculus, such as the intermediate value theorem and the extreme value theorem, which have practical applications in real-world problem solving. 6. Conclusion. Visual, host summarizing key points. Host, voiceover. In summary, continuity is a crucial concept in mathematics that helps us understand the smoothness of functions. It's about making sure there are no gaps, jumps, or breaks in the graph. Closing shot of a mathematical function graph. Host, voiceover. If you found this video helpful, please give it a thumbs up and consider subscribing for more math and science content. If you have any questions or topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching. Your channel name, and happy math learning. Script for a YouTube video explaining how to calculate limits. Introduction. Opening shot of a math textbook or a mathematical equation on a whiteboard. Host, voiceover. Welcome back to your channel name. In today's video, we're going to demystify the process of calculating limits in calculus. Whether you're a student struggling with calculus or just someone curious about the topic, stay tuned, because we've got you covered. 1. Understanding the limit concept. Visual, simple function graph. Host, voiceover. Before we dive into the calculations, let's quickly recap what a limit is. In calculus, a limit represents the value that a function approaches as the input gets closer and closer to a specific point. It's about understanding the behavior of functions near certain points. 2. Direct substitution method. Visual, equation on a whiteboard. Host, voiceover. The most straightforward way to calculate a limit is by using the direct substitution method. If you can plug the value a into the function fx, without causing any division by 0 or other undefined operations, then you can find the limit simply by substituting a for x in fx. Visual example equation. 3. Factoring and canceling method. Visual, equation on the whiteboard. Host, voiceover. Sometimes, direct substitution doesn't work, because it results in an indeterminate form, such as 0/0. In these cases, you can often simplify the expression by factoring and canceling common factors. Visual example equation. Host, voiceover. For instance, if you want to find the limit as x approaches 0 for the function fx equals x squared 4, x2, you can factor the numerator as x plus 2, x2, and then cancel out the common factor, x2, to get fx equals x plus 2. Now you can substitute 0 for x, and get f0 equals 0 plus 2 equals 2. 4. Squeeze theorem. Visual, Graph illustrating the squeeze theorem. Host, voiceover. The squeeze theorem is a powerful tool for calculating limits when direct substitution doesn't apply. It states that if gx, fx, hx, for all x near a, and the limits of gx and hx as x approaches are both L, then the limit of fx as x approaches O is also L. Visual squeeze theorem example. Host, voiceover. Let's say you're trying to find the limit as x approaches 0 for fx equals x squared sine of 1/x. By applying the squeeze theorem, you can show that the limit is 0. 5. Conclusion. Visual host summarizing key points. Host, voiceover. Calculating limits is a fundamental skill in calculus, and these methods we've discussed today can help you tackle a wide range of limit problems. Remember, practice makes perfect, so keep working on different examples to sharpen your skills. Closing shot of a math textbook or whiteboard. Host, voiceover. If you found this video helpful, please give it a thumbs up, and consider subscribing for more math and science content. If you have any questions, or if there's a specific math topic you'd like us to cover, please leave a comment below. Thanks for watching, your channel name, and happy math solving. Script for a YouTube video explaining the formal definition of limits. Introduction. Opening shot of a chalkboard or whiteboard with mathematical equations. Host, voiceover. Welcome back to your channel name. In this video, we're going to delve into the formal definition of limits in calculus. Understanding this definition is fundamental to mastering calculus, so let's get started. 1. Defining the limit. Visual equation on the board. Host, voiceover. To formally define a limit, we use the notation lim x(a) fx equals L. This means we're looking at the behavior of a function fx as the input x approaches a specific value, denoted by a. Our goal is to find the limit L to which the function approaches as x gets closer and closer to a. 2. The epsilon delta definition. Visual, mathematical symbols on the board. Host, voiceover. The formal definition of limits involves the concept of epsilon, and delta, delta. Here's how it works. For every positive number epsilon, there exists a positive number delta, such that if the distance between x and O is less than delta, then the distance between fx and L is less than epsilon. 3. Breaking it down. Visual, step-by-step breakdown of the definition. Host, voiceover. Let's break it down further. We want fx to get arbitrarily close to L as x gets closer to a. No matter how small we choose epsilon, we can find a corresponding delta that guarantees this closeness. Visual illustration on the board. Host, voiceover. In other words, for any epsilon 0, we can find delta 0 such that if 0 dot x a delta, then dot fx L epsilon. 4. Visual representation. Visual graph on the board. Host, voiceover. Visualizing this concept on a graph can help. Imagine a function fx and a horizontal line representing L. We want to find a delta such that for all x values within delta units of a, the corresponding y values, fx, are within epsilon units of L. 5. Practical examples. MPS TIN RES RTA S RC SCR SIN Visual examples of applying the definition. Host, voiceover. Let's apply the formal definition to a few practical examples to see how it works in action. We'll choose different functions and values of a to find the corresponding L and the required epsilon and delta. 6. Conclusion. Visual host summarizing the key points. Host, voiceover. So, there you have it. The formal definition of limits in calculus. Remember, this definition is the backbone of calculus and provides a precise way to describe how functions behave as they approach specific points. With practice, you'll become more comfortable applying it to various problems. Closing shot of the chalkboard or whiteboard. Host, voiceover. If you found this video helpful, don't forget to like and subscribe for more math and science content. Feel free to leave any questions or topics you'd like us to cover in the comments below. Thanks for watching, your channel name, and happy learning. Video script for a YouTube content titled Evaluating Limits Numerically and Graphically. Introduction. Opening shot of a math textbook on a desk. Host, voiceover. Welcome back to your channel name. Today, we're diving into the fascinating world of calculus to explore the concept of evaluating limits numerically and graphically. Whether you're a student looking to ace your calculus class, or just curious about the topic, this video is for you. So grab your notebook and let's get started. 1. What are limits? Visual, a blank graph with a curve approaching a point. Host, voiceover. Before we dive into numerical and graphical evaluations, let's understand what limits are. In calculus, a limit represents the value that a function approaches as the input gets closer and closer to a specific point. It's a fundamental concept that helps us understand the behavior of functions near certain points. 2. Numerical evaluation. Visual, a graph showing a function. Host, voiceover. Now, let's talk about evaluating limits numerically. To do this, you can create a table of values by plugging in numbers that get closer and closer to the point of interest. As these numbers get smaller, you'll start to see a pattern emerge which reveals the limit. Visual, a table of values. Host, voiceover. For example, if we're trying to find the limit as x approaches 2 for the function f(x) equals x squared 4, x2, we can plug in values like 1.9, 1.99, 1.999, and so on. As you'll see, the function's values get closer and closer to 4, which is our limit. 3. Graphical evaluation. Visual graph showing the same function. Host, voiceover. Graphical evaluation is another powerful tool for finding limits. By plotting the function and observing the behavior of the curve as it approaches the point of interest, you can often determine the limit visually. Visual, zoomed-in graph. Host, voiceover. Going back to our example, if we graph the function f(x) equals x squared 4, x2 near x equals 2, you'll notice that the curve approaches a y value of 4 as x gets closer to 2. 4. Common limit properties. Visual, list of common limit properties. Host, voiceover. It's important to note that there are several properties and rules for evaluating limits, such as the sum and product rules. These rules can help simplify the process, especially for more complex functions. 5. Practical applications. 2000. Visual, real-world application examples. Host, voiceover. Calculus isn't just a theoretical concept. It has practical applications in fields like physics, engineering, economics, and more. Understanding limits is crucial for solving real-world problems, where variables approach specific values. 6. Conclusion. Visual host summarizing the key points. Host, voiceover. And there you have it. We've explored the concept of evaluating limits both numerically and graphically. Remember, whether you're solving complex equations or analyzing real-world scenarios, understanding limits is a fundamental skill in calculus. Closing shot of the math textbook. Host, voiceover. If you found this video helpful, don't forget to hit that like button and subscribe for more math and science content. Feel free to leave any questions or topics you'd like us to cover in the comments below. Thanks for watching. Your channel name, and happy mathing. End.